We're going to learn in this video, we're going to get a better sense of what voltage means, what EMF is, and what happens in a resistor as energy is supplied and dissipated. So let's say we have a simple battery here connected to two resistors. Each has a resistance of 1 ohm. That's shown. These are connected in parallel. That's also shown in our picture. So let's say the EMF of this battery is 6 volts. It's a 6-volt battery, and we're going to imagine it has no internal resistance. 6 volts we could rewrite as 6 joules per coulomb, and if we compare the numerator and denominator, 6 joules and 1 coulomb, what we can deduce is that every 1 coulomb, the denominator, per coulomb, every 1 coulomb has 6 joules of potential energy when it's here at the left terminal. Okay. So 1 coulomb, there it is, and that coulomb's going to travel around our circuit. But it's not just alone by itself, it has energy, 6 joules of energy. So let's put 6 lightning bolts on the coulomb to represent the energy. Each lightning bolt is 1 joule. The charge travels around. The wire merely carries it from the terminal to the first resistor. No energy is dissipated in the wire, so we still have all 6 volts. Here it is, it gets to the 1 ohm resistor. Notice for a second, if this resistor is 1 ohms, and the second is also 1 ohms, 1 ohms, if they have equal resistance, then the amount of energy dissipated here will equal the energy dissipated here. In other words, this is going to dissipate half, and that will dissipate half. So it travels through from one end of the resistor to the other, and in the process, it loses 3 joules. See that? The amount of potential energy lost, then, is 3 joules, just like the picture shows. And then it travels to the next one, to the next resistor. And it loses the exact same amount of energy as it passes through that resistor. So the amount of potential energy lost is 3 joules. Then the wire carries it back to this smaller terminal where it has no energy left at all. But the battery uses its fluids to re-energize that charge and pump it back over to the other side. So the charge will actually come back over, and it'll have 6 lightning bolts again. And in the process of pumping it back to the position of high energy, giving it the energy, in that process, some of the fluid of the battery is used up. Now we can talk about potential energy, or it's much more convenient to discuss the voltage dissipated by this resistor and the voltage dissipated by this resistor. If this resistor dissipated 3 joules of energy, then we can calculate the voltage. There was 3 joules, and that was dissipated within 1 coulomb, and so the voltage is 1 volt. That's how many volts were dissipated across this resistor. And likewise here, we have 3 joules divided by the 1 coulomb that traveled through, and we get 3 volts. Now let's take a different situation. Let's imagine instead of having equal resistors, we have a bigger resistor on the left and a smaller one on the right. We have the same EMF, 6 volts, so every 1 coulomb has 6 joules when it starts here, and when it gets to the other terminal, it has no energy at all. So it loses all 6 joules in the circuit. The question is, does it lose all 6 here? Does it lose half here? What happens now that we have a bigger resistor out front? So imagine we have 1 coulomb, and it's at the it's at this small terminal. So that means it has 0 joules of energy. There's no bolts. The battery, whenever a charge is there on that end, it pumps it over to the other side and gives it energy. You see that? And then it starts traveling around the circuit. So again, it has 6 joules because it's an EMF of 6. So I've shown the 6 volts, but this time I've taken away the joules, just to make it a little clearer. So the energized charge is traveling around, and the wire carries it from the terminal to the first resistor, and it still has all its energy. Okay, so it keeps traveling around. When it gets to the first resistor, it's about to lose some energy. And here's how this works out. If the first resistor has twice the resistance as the second, 2 compared to 1 ohm, then the first will dissipate twice the energy as the second. The proportion of resistance to energy dissipated is fixed for the two. So here's what that looks like. It comes through and it loses 4 joules of energy. So now we have just 2 volts, 2 volts or joules remaining. And then it comes over here and it loses all of the remaining energy, which was 2 joules. Twice the resistance, twice the energy loss as compared to here. 2 to 1, 4 to 2. And then it's carried back over to the 0 joules, the 0 volt plate, the other terminal. So to make sense of this, let's switch again from talking about potential energy lost to voltage that's dropped. In the first case, the voltage is equal to the amount of potential energy lost, which was 4 joules, divided by the size of charge, which lost those joules. So we had 1 coulomb that came through, 1 coulomb, and lost the 4 joules, giving us 4 volts. Then that 1 coulomb came through this resistor and lost 2 joules. So the voltage is 2 joules divided by the 1 coulomb that passed through. And that gives us 2 volts. And what we notice is that the ratio of V over R, right, 4 over 2, that gives us 2. And the same ratio is what we see over on the right side. V over R is 2 volts over the 1 ohm. So for this resistor, V over R is equal to the same as for this resistor, V over R. They both equal 2. But wait a second. V over R gives us the current through that 2 ohm resistor. And likewise, the 2 volts over that 1 ohms, the V over R for the second resistor, gives us the current through the 1 ohm resistor. And of course, if charge is coming through that first resistor, then all of the same charge, all of the current, will also pass through the second resistor. In other words, the current through the 2 ohm resistor equals the current through the 1 ohm resistor. And that's why the value of V over R is fixed. So the bigger the resistor, the bigger the value of R. The bigger the value of R, the bigger the value of voltage dissipated across that resistor. If this thing went all the way up to 1 million ohms, then the voltage that it dropped would get really, really, really high, but would never quite reach 6, because there's only 6 volts in the first place for our charge to lose. So it can never dissipate more than what's being supplied, because there's nowhere else for that energy to come from.